everyone, my name is Natalie Gayoso. I am a research student for Anjali Mulchandani, and my research is on conducting a techno-economic analysis to determine costs of atmospheric water capture technologies. So I want to start off with the need of my research. So engineers have perfected liquid water treatment and made it safe, clean, and reliable. But for locations off the grid or locations undergoing a natural disaster like Hurricane Dorian in 2019, the only option right now is bottled water, and that's 400 to 700 times more expensive than surface water treatment or seawater desalination. Therefore, there is a need for clean drinking water off the grid that still provides that flexibility of bottled water. That flexibility meaning that you can bring it anywhere at any time and it's safe and it's ready to use without the cost and waste. So how else can we supply water off the municipal grid? One of those solutions can be through atmospheric water capture, which is a fresh water source, just like lakes, rivers, and groundwater. And the atmosphere has a volume of actually over 100,000 kilometers cubed. In addition, it has a few other benefits like 6 times more water than rivers. It has minimal waste and is universally accessible. So let's take a look at one of the most common atmospheric water capture technologies using refrigerant to compress vapor into liquid. So the diagram on the left, if you're looking at the blue arrow in this waste or in this water phase diagram, it demonstrates how atmospheric water harvesting works. Essentially, it takes water from the vapor phase and pulls it into the liquid phase. And the easiest way to do that is by cooling the temperature while keeping the pressure constant. And how a compressor technology works is shown on the right. The damp air comes in, it interacts with the cold refrigerant through the heat exchanger, and the moist air becomes a liquid and it gets collected in the water tank. And then that refrigerant is then recycled through to become cold again, and that process continues throughout the harvesting water process. And so now that I've explained a little bit on the technology, I want to get into my research objective, which is conducting a techno-economic analysis, also known as a TEA, with a range of cost models to understand capital and operational costs of AWC across different climate regions supplied by renewable energy and also regions connected to a grid. But first, what is a TEA and why is it important? First, a techno-economic analysis combines production cost modeling and customer financial analysis to provide decision-making insights to R&D specialists. So that process includes an R&D breakthrough, in my case, atmospheric water capture, then defining that concept, performing a cost model, then a financial analysis, and just refining that over and over again. And it's important because it establishes a common language between industry and then also academic researchers. So let's start with this process flow diagram of a compressor dehumidifier for AWC. The inputs for this compressor dehumidifier are humid air and temperature. And how does it work? Well, it runs off of power from various sources, either solar panels, wind turbines, or the electrical grid. And then it produces a certain amount of water in terms of volume of water in a day. And then we're going to perform a financial analysis by breaking down into capital costs first to purchase an entire unit. So let's get into the cost breakdown of the major components that make up a compressor dehumidifier, which include a heat exchanger, a refrigerant, an evaporator, a compressor, a condenser, and a fan. And for our piece-by-piece case study, we pulled cost data from a unit that harvests 16.25 gallons of water per day. And in the circle graph, it demonstrates that the heat exchanger is the most expensive at around $1,100, and the fan, the least expensive at around $50, with an end cost of around $3,000 for the piece-by-piece methodology. So when analyzing the piece-by-piece breakdown, I thought it would be good to also compare the cost of an entire unit. And for the dehumidifier that produces 16.25 gallons a day, the cost roughly is $2,500. So turns out the piece-by-piece approach is 18% more than the whole unit. And this raises the question, are we better off averaging costs of a whole unit rather than trying to piece together a unit ourselves? So right now we're trying to reconcile that decision and identify which method is most cost efficient. So I just briefly explained the details on capital expenditures, and now I want to get into operating expenditures and the cost of power draw per day. So similar to capital costs, we're also reconciling operating costs, but we're basing it off of information given to me by a company versus scientific analysis of a process. So on the left is a company spec sheet for a unit that produces 30 gallons of water a day and uses 1.2 kilowatts of energy. Now, how does this compare to thermodynamic calculations of energy to go from a vapor to a liquid? So if we're looking at the graph on the left, where it shows delta H, or latent heat, at roughly 30 degrees Celsius and 80% relative humidity, it's about 46 kilojoules per mole. And then on the right, if you're looking at Gibbs free energy, or delta G, it's around 10 joules per mole. So it turns out the 1.2 kilowatts is equal to 16.4 kilojoules per mole. And that number ranges in between the two. So again, we're reconciling to see which method produces the most accurate cost of power draw and then the most cost effective, depending on the capacity of the unit and then also the climate outdoors. So we started with these open boxes with no data, and then I just showed you the operating cost approach, which is the thermodynamic power draw and then the set power draw. And then I got into specifics on the piece by piece methodology and the whole unit. And then for the next steps, we're going to be looking at water treatment, the CapEx and OpEx costs, and then also how that water treatment process looks, which will result in the volume of water produced per day. So some last things to wrap up, I want to talk about the key takeaways. So in order to determine the capital cost of atmospheric water capture, we're reconciling a whole unit cost analysis and then also a piece by piece cost analysis with the major components that make up a compressor dehumidifier. And then we're also reconciling operating costs by looking at the information given by a company versus scientific analysis of a process and deciding which methodology is most cost efficient. And that's all I have. This project was funded, or is funded, by Pepsi and UNM and in collaboration with Arizona State University. And thank you.
Awesome, great job, Natalie.
I have one question. Are you planning to look at the efficiency of atmospheric water capture across like different climate, like arid versus semi-arid versus temperate, and how might that affect the cost? Because the thermodynamic change, right? And so once the thermodynamics change, then cost might change too.
That is very true. Exactly. We're going to look at that as well. It's one of the cost analyses that we're going to do. Most dehumidifiers have like a relative humidity that they capture the capacity from. So usually it's around 80% relative humidity, but I mean, in arid climates like New Mexico, we won't get that high. So we'll be doing a cost analysis for different climate regions for sure.
Cool.
I have one quick question. So I'm wondering if air quality, and specifically with particulates, if that will potentially contaminate the water you're capturing, and if so, if that will drive costs up because then you have to do additional treatment on the water.
Yeah, that's a very good point. We're going to be looking into water treatment, like the HEPA air filter, activated carbon, different methods to treat the water, and that will also change the cost of it.
I have kind of a left field question. When these kind of disasters happen, or a community either has or finds itself in a position where it needs these, like something like emergency atmospheric water capture, who pays for it? Like who's going to benefit like from the analysis of you saying like, hey, this is less than sending them bottled water?
Mm-hmm. Yeah, well, Pepsi's funding this research, so I think they're curious to see how much this is going to cost them, because if it's less money, then they're going to go to that route. I don't know who's going to pay for this in rural areas, though. I don't know, do you know, Anjali? Yeah, we don't really know.
Thank you. Great job.
Thank you.
One quick question. So how might this affect like regions, like terroir regions, right, where electricity is a factor? Is that something you consider?
Well, the goal is to actually make this off-grid. So using renewable energy, that's the ultimate goal. So we do want to not use the electrical grid, either just using solar panels or wind turbines to power the dehumidifiers or whatever technology we choose to capture the water.
All right. Thank you very much, Natalie.